board and get so that I can write. All right. You know what the mean value theorem says, right?
Yeah.
Pretty much. In other words, what the essence of it is if you have a curve like that,
right,
if you take the average slope right there, there will be at least one point on the x-axis whose first derivative is that same slope.
right.
In this case, the way I've done it, it looks like there's one there. So that would be a C. And it also looks like there's one about there. So this one would have two values.
Right.
Satisfies the mean value theorem. Okay, so what are we going to do with this problem? First thing we want to do.
So on the interval 2, 4. Wouldn't we do the f of b minus f of a over b minus a?
Exactly. Let's find out what the average slope is. Okay, the average slope is f of b minus f of a all over b minus a. Now what's f of b? F of 4. This is b. That's a.
4 plus 1/4 is.
We'll just leave it in fourths. 4 plus 1/4 is 17/4.
Yes.
That's f of b.
Okay.
What's f of a?
F of a is 10/3.
And b minus a
is 4 minus 3.
Okay. So that is our slope between the points 3 and 4. Mean
right.
The theorem says there has to be a point in there that is equal to that slope. Well, let's see. What's the best thing to do here? Let's turn this into twelfths, I guess. What do we got? 51 twelfths minus 40 twelfths, 11 twelfths. Okay. Now, what's the next step we have to do?
Next step we have to do is,
Okay.
I'm actually not sure.
Well, remember there has to be a point whose derivative is equal to that number. So
do we plug in 11 twelfths or?
No,
or we
take the derivative. What's f prime of x?
1 plus ln x.
The derivative of 1 over x is minus 1 over x squared. In other words, you can apply the power rule there. You're getting it backwards. The derivative of ln x is 1 over x. But the derivative of 1 over x is, just treat 1 over x as x to the minus 1, and you end up getting this. Okay? So, what I'm looking for is some c that's equal, excuse me, let me do it this way, to 11 twelfths. So now all I have to do is solve that. And when I say a c, I'm looking for a value of x.
Right.
In other words, this is the first derivative, correct? 1 minus 1 over x squared is the first derivative of that function.
Correct.
So we're looking for a point where that first derivative is equal to the average slope of the function between 3 and 4, which is 11/12. So we merely have to solve that. Now,
Okay.
what is that? That's 1 over x squared equals 1/12.
Right.
What's the answer? A, B, C, or D?
D.
What do you get for x if you solve that?
Well, wouldn't you multiply by x squared on both sides? Well, you get plus or minus root 12.
Okay. Now, they've got a -1 and a +1, which is our answer.
Well, it's whichever one's on the interval from 3 to 4.
Exactly, which is the +1. It's definitely not the -1.
That'd be D.
That'd be D, correct. Okay, so that's how you do those. Is you find the average, and then you take the derivative, and you set the derivative function equal to that average slope.
Right.
All right. Oops, hold on a second. I gotta remember to do it this way. Okay. Let's see if I can find the page in my book that has all of these power series. Yep, I got it. All right, this one. Do you have a page in your book that has a page of power series for elementary functions?
I don't have my book with me, but probably.
Okay. If you look on that page, it gives you the power series for e to the x. Ooh, and the power series for e to the x looks exactly like this one. That is not an answer, though. Here, let me look at it again. Oh, no. The power series for e to the x. Here, let me write it down because this will be useful. Hold on, let me get my writing tool up. So, e to the x converts to this power series. Not only converts to that power series, but that power series is equal to e to the x.
Right.
And we got x to the n over n factorial. So what is the difference between this one and that one?
Looks like it's shifted over a term.
Well, what would we have to do to our e to the x power? If we look at our answers over there, let's check this one out right there.
Well, it looks like it'd be e to the x squared because...
Okay, you're way ahead of me. I was just going to kind of look at them one at a time. It's not a, because a, I would have to multiply this power series by x, and I would get x plus x squared plus x cubed over 2 factorial, which is not what we're looking at. Oh, yes, it is what we're looking at.
Yeah, it is. I guess my guess was off.
Plus x to the 4th over 3 factorial.
So that is the right answer.
I think so. Yeah, even down to that right there. Because, That's going to be the nth minus 1 term instead of the nth term. Yeah, if you notice that 3 corresponds to a 2 factorial, that 4 corresponds to a 3 factorial, so the n must correspond to an n minus 1 factorial.
Right.
Yeah. And
So,
in all
yeah,
truthfulness, that's what these power series is. That's how they're used. It's not so much deriving the Taylor series or the Maclaurin series. It's using it once you get it. And being able to take things like that and turn them into power series. Or that, or even that. That last one's a good one, because the one integral that I know you cannot integrate is this. And the way you do it is by using the e to the x power series, and in place of x, you substitute minus x squared. No, I don't remember. But anyway, I don't know if you're familiar with this, but it's worth mentioning. The most accurate, have you ever thought about how they figure out what pi is?
No.
Well, it's an interesting question, right? In other words, you can't draw a perfect circle and a perfect diameter and divide the two. That's what the definition of pi is, but how do they actually come up with? Well, there were some old-fashioned methods back in the Greeks and Romans where they would draw polygons, many-sided regular polygons, fit them inside of a circle, and they could figure out the area, or rather the circumference of the polygon, and they just let it approach infinity, and that's kind of the way they figured out pi, but it wasn't terribly accurate.
Right.
It turns out that the best way is the arctangent. I'm not going to go through it, but just to point it out, the arctangent of x also has a power series, which is x minus x cubed over 3 plus x to the 5th, on and on. Turns out that you can calculate pi with the first 4 terms to an accuracy of 9 places.
Wow.
And that is the most efficient method yet discovered for calculating pi. And of course, if you want it out to 12 places, you just keep adding terms. That's the whole point of these power series. That's how you get pi to, I think I read the other day that they actually have it out to 25 trillion places now.
Wow. And
they get those by just keep adding on terms from these power series. So there is a purpose on some of these. I had another calc student ask me the other day, what's the point of these power series? And the only example I could think of to give her was, well, it's the only way we can integrate e to the minus x squared. But there are lots of other reasons or uses for them.
Right.
Just sitting here thinking, my first inclination was, how does this thing converge? But it does. Converges to x e to the x. I guess the wrong way to look at it is, I mean, you see why I'm wondering why it converges is because every x, if you have an x squared, is all you're doing is adding positive numbers that appear to be greater than 1. But that's not really true, I guess. You get to these factorials, the growth of the factorials in the denominator. Factorial growth is whatever you want to call it, it's as fast of growth as you can get.
Right.
If you take e to the x and divide it by x factorial, that's going to 0 as x goes to infinity. even though the numerator is an exponential. All right, let's see. Do you have another one on this page? No. Did you send me another page?
Yeah, there should be another page.
Okay.
Huh.
Is it anything you can verbalize? We got 10 minutes. These previous two, you actually probably could have verbalized them. If you can find one that you can verbalize, we can do it without waiting to get the picture. Should be able to find one there. You got any just straight derivatives or integrals? I don't know how many pages you have on your end.
I only sent two, but I don't know where the other one went. Oh well.
I didn't get the other one. Can you verbalize the second?
Yeah, I can verbalize this one.
Okay.
So evaluate the integral from 3 to 4.
Okay. One second here. I forgot to turn this back on.
Of dx over x minus 3, like x minus 3 squared with parentheses.
Let's write it like that. Right? Same thing?
Right.
Okay. How are we going to do this?
Well, we could separate the fraction into two separate ones, 1 over x minus 3 plus 1 over x minus 3.
Yeah, it's...
dx.
Well, we're going to use partial fractions, right?
Right.
Okay.
That's what I meant.
Okay. So we've got, let's go ahead and do that.
So a over x minus 3 plus b over x minus 3.
Now what?
Then a times x minus 3 plus b times x minus 3 equals 1.
Uh-huh.
But are we going to run into some problems?
Yes.
Because they're both going to equal 0.
We are. So... Now, if we group, we get x times a plus b minus 3 times a plus b equals 1. See what I did? I grouped the x's together and I factored out the x. And then I grouped the 3a and the 3b together and I factored out the 3.
Right.
Now, there is no x term up here, so I know that a plus b has to equal 0.
Okay.
And I also know that a plus b has to equal negative 1/3.
Right.
In other words, this number has to equal 1.
Right.
That's problematic also, isn't it?
Yes.
Mm-hmm. And that's no solution.
There is a answer for divergent on there.
Oh, really? Oh,
Yeah.
on the page as one of the possible choices. Before we
Right.
go there, let's think about this for a second. Because there is another method, I don't know if they taught it to you, instead of partial fractions.
I'm not sure.
Completing the square. Ah, hold on a second. What if we write this as x plus 3 squared? We don't need to use partial fractions. We can use the power rule, I believe.
Well, x minus 3 squared.
It's x minus 3?
Yeah.
Yeah, why can't we use the power rule on this? In other words, why is that not the natural law, or, excuse me, let's write it properly. X minus 3 to the minus 2 power dx.
Right.
Now, can I use the power rule? I think I can. I'm going to add 1 to the exponent.
Right.
And the derivative of the inside, and then I'm going to multiply or divide by that new exponent. And since the derivative of the inside is 1, I don't have to worry about chain rule applications. So this appears to be 1 over, or negative 1 over x minus 3 that I have to evaluate from 3 to 4. So help me evaluate it. What should I?
Okay, so 1 over 4 minus 3, so 1 over 1 is negative 1.
Okay, so that's the top.
Minus.
Uh-oh.
Yeah, that's going to be 1 over 0, which can't happen.
Well, that's going to be infinite, right?
Right.
In other words, if we do substitute 3 for there, we get 1 over 0, which is infinite, and we're subtracting a negative infinity. That's divergent.
Right. So yeah, that is why they gave a divergent on the 4 answers.
Well, let's look a little bit more at that one. I want to draw a picture of it, because we should be able to see why that's divergent. I don't get why it's divergent at the moment, to be truthful. It's not hard to graph. It's a parabola whose vertex is at right there, at 3. And it's a parabola that goes like this. Well, here's 4. This area is not infinite.
No.
What's this value right there? That is 1. Is that area less than 1 or greater than 1?
Huh?
Is the area that I've shaded in there?
Is it less than 1 or greater than 1?
Uh-huh.
It's 1 or less than 1.
Well, the rectangle would be 1. So it's definitely less than 1. Is it less than 1/2?
Could be.
Has to be, because there's the diagonal.
Right.
And since the parabola is curved, it's going to be less than 1/2. What are your possible answers?
Negative 1, 0, ln of 4, or divergent.
It's got to be ln of 4.
Okay.
Now, why is the question. Why were we not able to solve that integral? We just got a couple minutes here. We might as well stay on this one. I suppose if I said the integral of that, wow. How can the integral be ln? This one's a little puzzling. Maybe they meant for you to figure it out the way we just figured it out.
Mm-hmm.
In other words, maybe they meant for you to draw it. We know the area cannot be, well, it's not -1 here because when we drew it, it was clearly above the x-axis.
Right.
It's clearly not 0. And it's clearly not that. When you draw it out, I mean, it'd be one thing if, we were talking about a hyperbola and saying, what is this area right here between 0 and 1? I could see where that might be divergent because it goes all the way to infinity. In other words, you've got stuff approaching infinity, but in our parabola, we don't even come close to approaching a large area even. We know it's less than 1. It's less than 1/2. Unfortunately, what is the natural log of 4? Do you have your calculator handy?
Yeah, hold on.
It's greater than 1. Now I'm really confused. The natural log of 4 means e to what number is equal to 4? Well, that number has to be greater than 1.
Yeah, natural log of 4 is 1.3.
Yeah. Yet from our picture, when x is 4, okay. Let's go back here. I didn't do this anywhere close to correct. First of all, you can't graph it like I graphed it.
Okay.
I was graphing x minus 3 squared.
Right.
Well, this is 1 over x minus 3 squared. I'll tell you what, just real quickly, let me graph it on Wolfram Alpha. And you should be able to come up with the answer. This calculator allowed on this one?
I will. No.
No?
Nope.
Okay. Let's graph it anyway. 1 divided by x minus 3 quantity squared.
That makes sense.
Now, what do you think the answer is?
Divergent.
That's what I would say also. I'm not sure that's necessarily the answer. Just because something approaches an asymptote, there's a lot of functions that approach asymptotes that are convergent. The series 1 over x squared is a convergent series, and yet it does approach an asymptote. But if I had to guess just from the information we have, I would guess convergent.
Okay.
I mean, divergent is what I meant to say.
Right.
I'm going to look at this a little further, and especially since it's a non-calculator, we should be able to figure out how to integrate that. Maybe that completing the square. Have you ever integrated by completing the square on the denominator?
I have not.
The problem is it's a perfect square. I don't know why we would have to complete the square. I'm going to have to look this one up. We'll talk about it next time.
Okay.
Okay? All
Yep.
right, John. I'll talk to you on Wednesday?
Yes.
Okay.
Same time.
Yeah.
Thank you.
Wednesday morning, right, 9:30. Okay.
Bye.
Have a good one. Bye-bye.
You too.